let's go ahead and get started. I'm going to give everybody a few minutes. I wanted to mention some logistics that I didn't mention in concrete design that I kind of just thought of. So to be clear, I mean, the vast majority of people that are in concrete design are also in steel design, so it's not like, you know, have to make a super major announcement again. But you all are going to get a similar email about the schedule, similar email about, tests and so on and so forth. Let me say a couple things. First off, there's a few of you that probably have some outstanding like handouts, like I might have a homework assignment that I need to return to you. You might have some stuff on the cart outside my office, whatever, right? What I'm going to do is this, starting today, like literally today. I'm going to take every single physical thing that I have for every student that I haven't already handed back. I'm going to scan it and email it to them. Then I'll throw it away. I'll go to Fort Creek and kick it. It's like the Blair Witch Project. I just kicked that out in the creek. Hey, it's Friday the 13th. I got horror movies on the brain. Come on. I'm a horror movie junkie, so bear with me. For here on out, so for instance, you all have homework 4 that is currently being graded. And same thing in concrete design, there's a homework that's currently being graded. What I'm going to do is once that's graded by the TA, I'm just going to scan that as a PDF for everybody and just email it to you. And then from here on out, all future submissions will just be done digitally. So you all will just use like CAM scanner to scan your assignment and upload it. Is everybody okay with that? So that way, everybody will get all of the materials that they are outstanding, but I don't have to hand them to you, and you don't have to come to campus to get them. You know what I mean? You'll get them digitally. Okay, let's also talk about homework 5. You all have homework 5, and it was due Monday. I am going to respect the policy at Marshall, and I'm not accepting it on Monday. I'm going to wait until the day we come back, and I'm going to have it turned in on March 30th. We're going to turn that in digitally, okay? We're not changing that homework up. It's still there. I'm just going to accept it in 2 weeks. I do strongly advise you to go ahead and do it because, I mean, it's on welds. It's really easy. The longer that you wait, the longer that it takes for that material is going to seep out of your head. So I do suggest that you do it. I will take it, though, on the 30th. And I'll probably, for that homework, accept it at like 5 p.m. on Monday. So that way you've got a little bit of time. But again, no later than that. Does anybody have any questions about that homework assignment? That was the fillet weld on the angle. Okay. For the course operation here is going to be very similar to concrete design. We'll have the online streamed lectures, and then I will give you a problem, let's say like on Monday, and then it'll be due Wednesday, give you a problem Wednesday, it'll be due Friday, so on and so forth. The only thing that is going to be unique for us, as opposed to concrete design, is exam 2. We were supposed to have exam 2 next week. We're not doing that. But we're having that exam like as soon as we come back, okay? So what we're going to do for our first lecture in steel design when we come back is we're going to have our exam 2 review. It will still be on bolts and welds. It will be delivered online. 2 things. I know things are up in the air right now, so what I'm going to do is ask that you be prepared during that exam, or during that exam review, to tell me if there's any scheduling hiccups I need to be aware of, and be prepared to ask questions on that exam. Because I might give that exam Monday night. You know, I might post it at like 4 and have it close at 6, or whatever works for you. We've got some really weird scheduling coming up in the near future, so if you're going to have like other class commitments, if you're going to have work commitments, if you're going to have stuff like that, I need to know. So on March 30th, be prepared to let me know what's going on with your schedule, and we'll figure that out accordingly. We're still going to use the live stream effect, so if you need to put something in chat, put something in chat. If you need to say something on the phone, say something on the phone. But just be prepared to tell me what's going on. I mean, there's going to be people that have jobs. There's going to be people that have family commitments. There's going to be people that have commitments in other classes. And I'm going to try and do my best to not overload everything. But that second exam, I want to get that thing out of the way sooner rather than later, because the longer we wait, the longer that, I mean, it's on bolts and welds. I mean, March 30th, wait, we talked about bolts, I think, in February, and we'll be having it at the end of March, so I don't want to wait. I really want to get it done fast so that you all have the best chance at it. Okay, so be prepared Monday, March 30th. Ask questions about bolts and welds, and to let me know about your schedule. Does that sound like a plan? Next week, I will send you sort of a breakdown of what we're going to cover for between now and the end of the semester. That'll be sometime next week, and I'll have our lecture schedule ready, and we'll go from there. Sound like a plan? Ready to rock and roll?
Will it be pretty typical, like, for exams to be like, say, at night or in the evening?
It's possible, yes. I don't think because here's my point. I don't think because we are losing a week that we can afford to sacrifice 2 lectures, one for an exam review and one for an exam. I don't think we can do that. But at the same time, I want to make sure that I'm assigning the exam at a time that we can all do it, and that we're not, like, there's not that one person who's like, I had 6 things to do at that time, so I didn't get a chance to do the exam. I don't want that to happen either. So we're going to roll with the punches. So, and if I have to extend the deadline a little bit for this second exam to allow everybody to be able to take it, I will. So, but I don't want to push it back like 3 weeks. Like, we're doing it. Like, if it was me, we would do it Monday. So, does that sound like a plan? Are we good? Let's talk about columns. Let's get back into our column analysis example. I want to go back to this. This is the long and short. So if you remember, we've been talking about columns, and we've been talking about how real column behavior deviates from ideal column behavior because of really 2 parameters. Remember, ideal column behavior is what we can derive using differential equations and stuff like that. But it doesn't account for 2 things. It doesn't account for geometric imperfections, and it does not account for the presence of residual stresses. As such, these expressions in the manual take all that into account. So the AISC column curve, we call it the AISC column curve because when you plot it, when you plot it, this is FCR, this is KL over R, it looks like that. It looks like a curve, So that the AISC column curve is plotted using the following expression. Okay? So what I want to do is I want to go back to this example that we were looking at. This was example 15A. And I want to determine the capacity of this column just straight up using the equations in the manual. Okay, and this is what we were working on last time. This was the problem. And so let's just recap where we had left off. We had a 14 by 90. We had looked up all of the properties. We determined whether or not local buckling was going to be an issue. We found out it was not. And so we could look at section E3. Now, before we started using the column, the AISC column curves, we had to determine which slenderness governed. So along the x-axis, we had one segment that was 35 foot long and had a K value of 0.8. But along the y-axis, we had 3 segments. One was 10 foot long, one was 15 foot long, and one was 10, that each had differing K values. So what we did is we just took each segment one by one and computed KL over R. KL over R for the X segment, KL over R for Y1, Y2, Y3. And then for each of these, we just looked at all of them and said, which is the worst case scenario? The worst case scenario, bless you, the worst case scenario is always the one with the largest slenderness. The larger the slenderness, the weaker the column, because a slender column is a weak column. So when we're trying to determine capacity, we always look at the worst case scenario. And so we found that KL over R that we need to use for design purposes was about 54.72, right? So everybody okay with that? All right. Now, so method 1 says use the AISC column curves. And here's how the AISC column curves work. Okay, the first step, you need to compute FE. FE is the elastic critical buckling stress, or the elastic buckling stress, which is pi squared E over KL over R squared. Okay? Now, this is not the capacity. This is just a useful term that we will use to determine the capacity. So we have pi squared times what's E? That's right. I will burn that number into the back of your head whether you're at home or not. 29,000 KSI for steel. And then KL over R is 54.72. So 54.72 squared equals what? $95.59 what? KSI. Do I have a second on that value? Okay. Now, I think you should be able to look at that value and say that's not the capacity. What was the yield stress for this column? What's FY? 50 KSI. So right on its face, you should know that there's some limits to this formula because the yield stress of the column is 50 KSI. There's no way that under buckling it's going to hold up 96. That doesn't make any sense. It can't hold up more than the yield stress for a column that's 35 foot long. That doesn't really make a lot of sense. So that should tell you a little bit of a limit. Okay. Now, next thing that we're going to do is we're going to compute 4.71 times the square root of E over Fy. So that's 4.71 times the square root of 29,000 KSI over 50 KSI. What is that? $113.43. Right? So let's be clear. KL over R is 54.72. 4.71 square root of E over Fy is 113.43. Do I have a second on that calculation? Okay. I'm going to have to get used to, do I ask for seconds on calculations on the live stream? I'm going to have to get used to that.
Unmute it, yes.
I'll have my cat with me maybe if I do it from home. I'll ask, Rugen, are you good? Make some face at me. Okay.
You're going to be having cameras for this lecture?
Yeah.
Are we going to see you talking to your cat?
If my cat crawls up on the desk, that's it. Well, you might just hear her in the background. She'll be like, oh! It'll be cute. All right. This is going to be fun. Okay, so keep in mind, remember, KL over R is the same thing as saying LC over R. LC is just the critical buckling length, so it's the same thing. So the reason why we compute 4.71 times the square root of E over Fy is because we compare that against KL over R. If KL over R is less than or equal to this, then we use this expression. If it's greater than, we use this expression. So which one do we use, the top or the bottom? The top one, right? KL over R is 54.7. This is like 113. So 54.7 is less than that. So this is our expression. So our FCR so therefore our FCR is 0.658, and let me be clear, this is an exponent. Fy over Fe times Fy. So that equals 0.658 raised to the 50 KSI over 95.59 KSI times 50 KSI. And so what is that? All right, does anybody have an answer for this?
40.17.
40.17. Hold on. My pen there. KSI, do I have a second on that? Remember, that fraction is an exponent, okay? So therefore, my phi PN is 0.9 times FCR times AG, which is 0.9 times 40.17 KSI times, now what was AG again?
26.5.
26.5 inches squared. So what's phi PN? So let's just do one decimal place, 958.1 kips. Is that okay? Anybody have a second on that? Okay, so method one, we found that phi PN is 958.1 kips, okay? So in other words, 1.2 dead plus 1.65 has got to be less than that. And method one is you just calculating it, just using the equations. Sound good? Okay. Now, method one is sort of like the push mower, right? Method two is your riding mower, okay? So it's like your lawnmower analogy. Method two is a lot easier. And you definitely need to understand how to utilize method two, because method two is how we design columns as well. All right? But is everybody okay with method one? All right, yes?
So that gives us our capacity, like anything under that amount won't cause the column to buckle, and anything over will?
Yes, yes. As long as your factored load is less than that, the column is safe. Yes. So that's your capacity. So if you had 1.2 dead plus 1.6 live, and that came out to be like 920 kips, you'd be fine, because it takes that much to fail the column. Yeah. So everybody okay with that? Okay. Now, let's look at method number two. Now, I want everybody to open your manual, your AISC 15th edition steel construction manual, that I know everybody brought with them. Of all days? Of all days.
You can bring my bag today.
Sir!
Completely different. So I was packing for Lexington this weekend and
You're traveling?
yeah. It's been in the works for several months. So. keep this
I
here.
haven't traveled yet.
I'm gonna keep it at distance.
Okay. I need to flip papers.
No. I'll trust you. Okay, I want everybody to turn to table 4-1. This is going to become one of the most important tables that we use for design. Okay, now if you look at the table, you'll notice there's actually a lot of really good information that's listed here for a given column. For instance, if you look at the very bottom of the page, you'll see like the gross area, the moments of inertia, so on and so forth. There's a couple values that might be listed that don't really make a lot of sense, like an Rx over Ry ratio, and that'll become very clear here in a second. It is a very, very important tool for design. In fact, the way that we design columns is to use this table. There's really no way to design a column without it. See, design for columns and beams is going to be way different than it was for bolts and welds and tension members. Like with tension members, you would just solve for the area. You would say, okay, the area is 9.6 and just pick a section that works. It's not going to be the case here with columns and beams because the math is so funky, there's no way to do that. You have to use these design aids. One other point, if you haven't already done so, put your tab in this one. This is a very, very important guide. Now, let me explain how this table works. I want everybody to look at the column on the very, very left of the table. And what does it say? Like somebody read that out for me. Like this right here. The one where the text is tilted. What does it say? Read the column on the table. Like this stuff.
Effective length LCT with respect to least radius of gyration RY.
Okay, so let me explain what that means. What the table is doing is everything that we just did just now in the example we just did, the method 1, it's doing method 1 for all these columns. It says, well, what if method 1, the column is 9 foot long? Here's the capacity. What if the column is 10 foot long? Here's the capacity. What if it's 11 foot long? Here's the capacity, and so on and so forth. So this is just an Excel programmer's dream, just taking all these capacities and doing it all at once. But the disadvantage is that that column reports the capacities assuming that the weak axis governs. Okay? In the problem we just did the weak axis govern? No, it did not, right? The strong axis governed, right? Because we did all of our four, like the KL over R for the x-axis, KL over for the y-axis. We found that the x-axis governed. So how do you use this table if the strong axis governs? Here's how you do it. What you do is you ask yourself, okay, let's take our KL over R's and set them equal to one another. And let's ask ourselves, well, what would this need to be using these properties? So multiply both sides by Ry, right? So right? Just put that over there. If I'm multiplying by a fraction, that means divide by the reciprocal. See that? What is it? That Rx over Ry in the table? You see that? That's where it's coming from. So what do? We take our strong axis length, we divide it by Rx over Ry, and interpolate accordingly. Let me show you how we do that. So first off, again, everything's listed here on the bottom. So here's the thing. I think the easiest way to illustrate that is to just do the problem. Okay. I know that it's like, okay, we got interpolation, this Rx over Ry, it's a little weird, don't really understand it. Don't worry. This is actually pretty doable. This is the problem that we just did, right? Okay? Let's take this problem and let's compute the capacity using method 2, in this case using table 4-1. So maybe the first thing you ought to do is turn and find the W14 by 90. So if you look on the top, you should see, like it says W14 by this, W12 by this, find the W14 by 90. Oh, went too far. Was anybody able to find it? What? Say again? 4-16. So, help me out. What is Rx over Ry for this column going to be? Say it again.
1.66.
1.66. Everybody okay on that? Okay. So, in order to use this table, what I need to do is I need to look at two quantities, okay? The first thing I need to look at is KL effective, which the way that we compute that is using that formula up there, KX LX over RX RY. So help me out with that. For this problem, what was KX and LX for this problem? I can scroll up a bit.
0.08 for K is
0.08, and then the length was, you can leave it in feet right here,
35.
35. So this is 0.8 times 35 feet over 1.66. And that equals what? .87 feet. Do I have a second on that? Okay, all right. Now what I want you to tell me, what is the worst case KL in the Y direction? I'm asking you. What do I mean by the worst case KL? Well, we're thinking of columns, right? Columns, the worst case for a column is the case with the largest slenderness. So of these three cases, here, here, and here, which one's the worst one? Okay, Y2. Largest K value, largest length, right? So for that KY, we have a K of 1 and a length of 15 feet. So would this be 15 feet? Is that a fair statement? Does that make sense? Am I going too fast? Okay, all right. So I have a KL effective of 16.87 feet, and I have a KLY of 15 feet. So a way that you can think of this is the strong axis, and this is the weak axis. If you look at the table, what does the table say? Effective length with respect to the least radius of gyration. See, the weak axis, we can just look at the KL value. With the strong axis, we have to divide by that Rx over Ry. We do that so we can look at these two numbers and compare apples to apples. We can't just look at KL in the X direction and KL in the Y direction. We have to adjust this value because the table is built off of the Y-axis. Does that make sense? Now, of these two, which is the largest? That one, right? So I propose that this one governs because that's the largest. But that shouldn't be all that surprising. We already figured that out. We did that in the last part. When we did KL over R for each of the segments, we found that that was the highest one, right? So all that does is just further justify our calculations, right? Just shows that what we did before made sense. In method 1, we found that KL over R for the strong axis governed, and in method 2, we found the KL for the strong axis governed. That better be the case in both cases, otherwise you did something wrong. Sound good? Now, here's the thing. So, since this governs, I want you to tell me, look up in the table and tell me what's the capacity if the length is 16.87 feet. You can't do that, right? The table doesn't list the capacity for 16.87 feet, but what does it list? There you go. So, what that means is this. What is the capacity for a KL of 16 feet? I want to make sure everybody can find this. 979 kips. Did everybody find that? So somebody else tell me what's VPN for KL of 17 feet. 955 kips. Is everybody able to find that? How many of you remember how to linearly interpolate between 2 points? Guess what? You need to linearly interpolate this. So what I'm asking you is, you know the value for 16 feet, you know the value for 17 feet. What is the value for KL is 16.87 feet? Anybody remember how to do that? Let me show you.
I always forget. I have to do it in almost every class, but I always forget it after I learn it. I don't know why.
So what you're going to do is you're going to take the first value plus the slope, so change in y, change in x, times the change in x.
You don't like the Casio?
If you do it in your Casio FX 115 ES Plus, I'm not going to knock you at all. Anybody have an answer for me?
958, 112.
You should get the same answer every time. Now, in fairness, You may get a little bit of a different answer, plus or minus, like that might be 958.2 or something like that. But you should get the same answer. The difference is going to be rounding because the table is only so accurate. It reports all of the quantities to 3 significant figures. So as a result, if you're tracking decimals, you're going to get differences in answers. But that's basically it in a nutshell. Does that make sense? Any questions? So if you understand that, first off, I'm going to tell you, I'm skipping method 3. Time consideration, we don't have. And if you have 2 methods, you're good. So don't worry about that.
So neither method is better than the other.
What's that?
So like neither method is better than the other one.
No, that's a fair question. The answer is no. They both work to determine capacity, but what I highly recommend is that if you've got the time, if you've selected your column using method 2, check it using method 1. You should get the same answer. Okay? Now, we don't really have time to cover this today, but what we end up doing for a design problem is the following. We use table 4-1. So what we do is we factor our load, and we use the capacity tables to pick what are called trial shapes, okay? And so what I mean by trial shapes is that you pick a section from each family. So you'll pick, like, for instance, let's say I have a factored load of 500 kips. So based off 500 kips, pick a W14 option that works. Pick a W12 option that works. Pick a W10 option that works, a W8. And then from all of those sections, you just pick the one that's the lightest. Now, one of the things you will find when you use this table only lists W14s, W12s, W10s, and W8s. There's a reason why. W14, 12, 10s, and 8s are the I sections that are the most square, okay? And for a column, you want it to basically have an aspect ratio close to 1. You want it to be about as big this way as it is this way, okay? Once you start getting into W18s, W21s, W24s, those are the sections that get much deeper, okay? And those are the sections that are more appropriate for beams, okay? So there will only be W8s, W10s, W12s, and W14s in table 4-1. So from that, you will pick given options, okay? So to give you kind of an idea, let's keep it simple, okay? Let's say you had a factored load of 600 kips. Let's just do one real quick. Let's say you had a factored load of 600 kips. And let's say that the KL in the Y direction is 15 feet. Okay, somebody help me out. What would be the first W14 option that you would pick? And what I mean by the W14 option, I want you to find the lightest W14 that would resist this load. I literally just made these numbers up, so we'll see how well this works. Well, I want to make sure I pick some numbers that make sense. Okay, I did. All right. Anybody have a W14 that works?
W14 by 68.
The W14 by 68. And why did you pick that? What's the capacity?
BPM is 608.
Is everybody else able to find that? So somebody else, tell me the W12 option that works. Now, why did you pick that? What's the BPM?
663.
Say it again.
663.
Okay. Give me a W10. Somebody else. Why did you pick that? Okay, give me a W8. And it's possible that there is no W8. That's possible as well. So, no W8s. So, here's the thing. If this is all the information I gave you, right off the bat, there are 3 options. Of those 3 options, which one do you pick? I'm asking you. If you had to spend money on this project, which one would you pick?
So W14.
Why are you saying the W14?
It's the closest to the 600.
Okay, all right, now this is a great discussion. You're picking this because it's the most efficient, right? But you're wrong.
W12 by 65,
Why?
it's the smallest.
It's the lightest. See, this is something you're going to find with columns. Efficiency stops mattering as much. Like the PU over the VPN, the structural engineer's thinking, well, yeah, 600 over 608 versus 600 over this is least efficient. I don't care about that, right? I don't care about that because this is the less hit on my wallet. That's less steel, okay? So from all of your options, you choose the one that's the lightest, not the one that's the most efficient, right? Okay, so that's my first point. My second point, and this will be what we start our online lectures on when we come back, is this assumes that only the weak axis governs. What about the strong axis? Okay, so you look up sections based off of the weak axis. But what if I have a strong axis of like 32 foot? What do I then do? Well, for each one of these options, I select them based off of the weak axis. I then need to use table 4.1 to see, well, do they work for the strong axis? So what you might find is, of each of these options, this one might not work because about the strong axis, it fails. And then you have to say, well, what about this one and this one? And maybe you find that both of them work, in which case you could pick either one of them. I'd probably pick that one just because it's, smaller, But it doesn't, just because you have all these trial sections, you choose them based off of the weak axis. You still have to go back and verify the strong axis, okay? So, to be clear from our online lecture standpoint, that's going to be our next topic when we come back, and then it's beamland for the rest of the semester. So yeah, that will be what we do. Did that make sense? All right. All right. Here's, again, my advice. My advice to you is to get homework 5 done sooner rather than later. I am not taking it up until Monday, March 30th, but I am going to take it up. Okay? On Monday, we will have an exam review session, and that Monday we will schedule exam 2 to be conducted online outside of class time, probably in the evening, and we'll make sure that everybody has enough time to take it, contingent upon your work schedules or family arrangements or whatnot. And then starting Wednesday, we'll do column design, and then for the rest of the semester, it's beamland. Although we'll see if column design takes us into Friday as well. I'll look into it. So.
I think you're in my class too, right? Yeah. Pavement. Yeah, we have a pavement design exam due 11:59 p.m. on Monday.
March 30th?
Oh, no.
No, it's
Oh.
due this.
Okay, never mind. I was thinking this pavement. Sorry. Keep going.
I don't really have anything else, but that stuff, please, keep track of it, because when you come back Monday, I need to know questions on bolts and welds, and I need to know what your availability is on timing and so on and so forth. Does that sound good? Like I said, we will move into a problem per lecture homework schedule. So like On Wednesday, I'll give you a problem that'll be due Friday. Friday, I'll give you a problem that'll be due Monday. And it won't be like a full-blown assignment, it'll be a little mini problem.
So Monday, March 30th, we're having the review in the morning and the test in the evening.
Probably, yeah.
Okay.
And we'll figure out a time slot that works for everybody. So I will send you an updated schedule for each of my courses in the near future. One last thing, I'll go ahead and mention this. Advising is coming up. Like, you all do have to pick classes for next semester. What I'm going to do is I'm going to make myself available via phone for all of my advisees, and we'll literally talk on the phone for 15, 20 minutes, and we'll release your advising hold. But I'm going to be using a client that allows my office phone to be picked up at any location. Like, I can be home 30 minutes away and talk on my office line, even if I'm not on campus. We can do Skype sessions, we'll do whatever to ensure that you're moving forward. But that's coming up sooner rather than later. The university moved the drop date for classes to April 3rd, so you've got more time if you need to drop a class. But you are going to have to sign up for classes next semester, so that's coming up. So as the schedule gets released, we will also send you the info about Capstone for next semester. You'll be signed into it, like you won't need to register for it, but keep Capstone time slot open. So, also, there's a chance that we move you into because we're making some curricular adjustments to make it a little easier on you, but they're going through the university approval process right now, and things are a little fluid right now. So we'll keep you apprised, and the last thing, you all aren't going to have a problem one way or another. Like, you all are fine. We're the ones who got to work. So
about Capstone, you said that we're going to be assigned into the Capstone, right?
that's the plan right now, yes.
Okay, I just want to make sure that I've got the requirements, or I will have the requirements.
You will know, I will send personalized emails to every student eligible for Capstone, and that email will say, you're fine based on the class, if you pass the classes you're in now, or it will say, you're fine as long as you take this next semester or that next semester, so on and so forth. Every single individual student will get an email as to what they need to do. You'll know, I promise. We did a big analysis to figure out who's eligible for what, so.
So I'm going into 5 years now, I just want to get out.
Listen. I'm not talking about you, I'm just talking about, our job is to get you all out of here as quick as possible. You should see the analysis I did for Capstone. It's a spreadsheet that's ginormous to figure out who's eligible for what. We got you. Any questions? So, in case this is our last face-to-face meeting for the semester, very well could be. It's been an honor. Although we're not done, but I am available by email. I'm available by my office phone. I will get on Skype sessions one-on-one if I have to. We'll do what we need to do to work through this, okay? We will figure it out. The one thing I would say is please make sure that you're checking your email regularly, that you're checking your Blackboard regularly. We are all in this for you. You are our number one priority right now. I'm telling you. We got you. We'll get through this. Sound good? Everybody be safe. I guess it's not a vacation for us, but the next week is, I guess, some time off for you. What that means is stay clean, stay safe, stay hygienic, stay away from large groups of people.
Try.
You especially, after that comment.
I said you were still in good.
That's all I got, everybody. I'll see you.
This is the university story.